and reduce the access paths for a set of 3 queries by using a global temporary table, okay, to simplify the process. By using a global temporary table, we can reduce the number of times we have to access the original data with the 3 queries. We had 3 queries that are labeled A, B, and C in our example. And we notice that in all 3 of these, they have a common portion of the query. We're going to query the sales, the times, and the customer table. Doing a 3-way join is an equal join between all 3 tables, and we're looking for the day name from the time dimension, which is Friday. And we're going to compare what was sold on Friday for a particular country code. We also want to know what was sold on Friday, because this is basically the same part of the query that was in the example above, but now we've changed, instead of what was sold in a country, what was a particular product category. We don't know what electronics we sold. And also we're looking at a promotions with the same initial query. This opens up the possibility of creating a global temporary table, okay, to store the first portion and then query that table to answer all queries. It would save us 3 passes that join the full 3 tables together, okay, and pre-join them in a global temporary table to express part of the query and add the extra predicates afterwards. So let's have a look at these. We have some demo output to have a look at them. So taking a look at 18.1, which is our first pass, what did it cost us to do these without the global temporary tables? I'll go pick it up. So we go through and do an example of just executed in the way they were originally wrote. We're looking for the product ID and Friday of the equal join where the day name is only Friday. Then we do the second query, which was we showed on the board in the third one, so nothing new there. And we have a look at the output just to see how they actually performed. Okay. When we did the first one, we had to touch 1785 blocks in memory to return a single row, which was the sum of the amounts sold. We're calculating a group function. We used an interesting join to do that. They were able to find some indexes to help out. Then we did the second portion of it, okay, which was the query against the same data, but now we want to know the product category instead of the country code. And it cost us this many logical reads. We note the first one was fairly quick, but it's still getting into, this is starting looking more data warehousing like. We expect that pure OLTP queries should execute in a minute. This is something we do on a data mart or a data warehousing to do some analysis of what we sold. Based on Friday is maybe a more popular date to sell, to purchase things by customers, or Saturday than perhaps a Monday. Okay, and this one took almost 2 seconds also, 1.1 and 65/100ths, and it cost us this many blocks to have a look at. When we have a look at the final, the next one, we're looking at the promos instead of the electronics. Once again, we're looking at over 1 second to execute. And we had to touch this many rows, so we ended up passing through all of the data 3 times. By using a global temporary table, where the definition can be persistent, but the life of the data can either be a transaction or the session, depending on what's convenient for us. We could make it session so it sticks around for the life of a session, and then we could reuse it multiple times, independent of the transactions we were working on. So in this example, we're going to create the global temporary table that has the basic query that everybody uses, all three query users in it. Okay, once we create this global temporary table, we're going to use it as part of our query. Okay, and the global temporary table does the join of the sales and the time table to get the equal join, because that's the stuff that is common. The extra information we're getting from additional tables. So what we're going to do is create that global temporary table. We happen to call it, when we created it, the sales_Friday, because that's what it represents. And then we're going to join sales_Friday to customer table to look for a country code that the customers are in. How much did we sell in a particular country? Then we're going to do the same thing to ask for the electronics. We're going to join the products table to our sales Friday to find the electronics. Okay, and what we're hoping by doing this once and using it 3 times, we get an overall reduction in the resources to execute the query. Do this piece once and use it many times. And then we do the third thing. We join the sales Friday, our global temporary table, to the products promotion to answer the question, how much do we sell on Fridays for a promo category of TV sales? We have a bunch of TV sales in that. And let's look at the output of this. Okay, so we build the global temporary table, and it costs us a certain amount of work, okay, to do that, to process it. And then we start using it in our queries, okay. So we're going to join the Fridays to the customers to answer what did we sell in a particular country. And the first thing we notice, we have a nice reduction in time, and even more, we have a reduction in the I/O, in the blocks we have to touch in memory, the logical I/Os we need to do to solve the query. So this one, instead of taking over 2 seconds, we now complete it in less than a quarter of a second. 0.25 would be a quarter of a second. So it was a nice increase in performance. When we do the second query, we access our global temporary table and the products table, and once again we get a nice reduction, once again well under a quarter of a second, and a reduced number of logical blocks we need to do. And then finally we do the last one to get our promo character by joining the global temporary table with the promotions table. And we were able to complete this in less than a second. So they all took almost well over a second each. The sum of them is less than a second this time. So we've seen a substantial reduction, and we get the equivalent reduction in the number of buffers we have to touch in memory. So we see a substantial reduction in the overall processing time for these operations. Very nice. A lot of times global temporary tables are very useful for doing complex processing and saving a portion of it and reusing it if we have related SQL. Okay, next up we want to have a look at using the with clause. It's another way of rewriting a group, a very large complex query that has a group of subportions in it. We have a portion up here that is doing one set of processing. We have another portion here, okay, and then another complex piece down here. Could we make this easier? Right, and the with clause allows us to find repeating groups within a particular query and replace them with a single piece of code that we call many times with the with clause within it. And what it does is really treat it internally, the thing we specify in the with clause that's being used repeatedly, it gets actually treated internally as an intermediate result table generated once and used in multiple places within the SQL statement, just as if it was a global temporary table, but you don't have to declare it up front. It does it internally within the SQL statement. That allows us to get more efficiency in the statement. It's just another way of rewriting the statement to get efficiency. So let's look at some examples around this. So for 19, we have our SQL statement. Okay, so what we're going to do is rewrite the complex set of statements we had previously as a statement with a with clause. So we're calling the with clause the sales number, and this is the select. We've taken out of the subportions and are going to express once. Okay. If you're interested in seeing what it would like before, you can. There, the notes are on the slides, and then we're going to use this sales number in a number of places throughout the query. Okay, so we use it once in this portion of the query, which is expressed as an inline view. We're using up here the sales number that we pre-calculate. It executes this as a separate SQL block and stores the results as an intermediate and then uses it where it needs it. Calculate it once, use it in a number of places. We use it in the second chunk doesn't use it, okay? The third chunk should use it. So we're using it repetitively throughout the query, okay, in a number of places. So calculate it once and use it a number of times. And having a look at the performance of this, we'll take a look at it. Okay, this is looking at the first query in 19 I was supposed to be doing. Sorry about, we didn't give you, we just showed you how to rewrite it. So we didn't actually show the output for it. We just demoed how you could rewrite it. By demoing it, you get the same sort of performance benefit that we saw with the global temporary table, except it's only being reused within the one statement. Its scope is just within the statement, but we can get the same performance benefit. The advantage is you don't have to create the global temporary table. The disadvantage is the global temporary table can be used for multiple independent SQL statements. This you have to be able to rewrite it as a second statement, very complex. And it also simplifies the writing of the statement. I've personally found when I wrote with these, it takes a little bit of use to thinking about using the with clause, looking for something that's repeated as a subquery used throughout the query. But once you do, you can get a substantial performance increase from them. So simplify your query. And you can see a net improvements in the performance of them. But we didn't actually measure the performance of that one in this case. The next one is having a look at partition pruning. And we're going to move over to the board and have a look at this on the board, discuss partitioning for a moment or two on the board, and then we'll come back and have a look at this example just to put it in context. We sort of mentioned we weren't going to look at data warehouse and look at partitioning, and then we put in an example. To understand that, we need to at least understand a little bit of partitioning. You may know far more than I'm going to discuss. This was intended to give everybody who hasn't seen partitioning a little idea of how it works and how it do. So I could have a very big table that becomes difficult for people to administrate. Bigger the object becomes, it becomes difficult. We have customers that have single tables that are in the multi-terabyte range for their data warehousing applications and other applications. Take the big thing and apply the divide and conquer theory to it. Break it up into smaller pieces. that are easy to work with, and we could break it up into, and we call these smaller pieces partitions. Maybe this is sales for a year and I do it by quarter. So these would be my quarter names. Okay, so I have 4 quarters in a year. If I got one of the quarters right, I would have. Okay. And these would be range partition. We support a number of partitioning types. We support hash partitioning, list partitioning, range partitioning, then different combinations and interval partitioning. So if you get interested in that, we have a very nice 2-day class. Partitioning tends to work with larger applications, or quite often the data warehousing, but we have a very nice 2-day class on partitioning that talks about all the partitioning options for the table as indexes and how the optimizer can take advantage. But if these are range partition on date less than we might have 4 dates that represent the end of each of the quarters. And then anything that is less than the first quarter's date goes into partition 1. When I insert, when I do DML, anytime I write the application code, I always use the big table. We do have syntax to use the partition name, but if you use that, well, now if somebody repartitions the table, you got to change your application code. That leads to a lot of maintenance. Much better to do all of this in here. And if we insert a row, it has a date on it, the sales date, if this is a sales application. The optimizer will figure out which partition. It either go into this one, if it's less than this value, if it's less than this value, but not less than this, then what's left over goes into here. So they're range partitioned, a continuous range. Some go into here, some go into here. Convenient for administration if they were all the same size. Then if I have to export import, I can export import by partition. If 4 doesn't make it small enough, you used to have an upper limit of 64,000 partitions. It is now 1,000,000 partitions. So you can have lots of partitions, more than I think anybody will practically use. And what is very cool is the optimizer can take advantage. If it's stored as one big table and we don't have an appropriate index, we may have to do a full table scan on the whole table. And that's an expensive operation. If we have a partition table and we happen to include the partitioning key as part of the predicate, then the optimizer can reduce the partitions. If I give it a single date, I'm looking for orders on one particular date. If this is a sales application, the optimizer knows it's got to be in one. One date only exists in one partition. It's either going to be in Q1, Q2, Q3, or Q4. What that means is that it only needs to do a full table scan on a quarter of the data in this example. It can throw away 3/4 of the data. If I give it a range of dates, they may fall into one partition. They may fall into multiple. So in that case, if they fell into both Q2 and Q3, then it could eliminate the Q1 and Q4 and look at these 2 partitions. And of course, if I have more partitions and I can eliminate it based on one date, I do more fine grain. If I happen to have 100 partitions, which is not unusual, and then if I only find the data in one, I just reduced 99% of the data. I just need to do a full table scan on one. If I need to look at 5 out of 100, I've reduced 95% of the data. I only have to look at 5% of the data by doing a full table scan on individual partitions. So now that we've had a little bit of background on partitioning, we're going to go back to the slides and talk about this slide. Okay, so this is example 20, partition pruning. So how can we take advantage of having partitioning? Okay, so we wanted, in reality, the sales table in the sales history schema is partitioned automatically. What we wanted to do is compare that to a non-partitioned version. When you do that, it ends up, depending on the predicate, we're looking for a range of time. It ends up doing, if we don't have an appropriate index, it ends up doing a full table scan on all the data. And in this case, they're returning 20,000 rows out of their sales table, which has just under 1 million rows in it. Okay, so we have some examples of looking at this, looking at 3 cases. We actually can create this version that has no partitioning to show doing a full table scan, and then using the same because it's as a partition table, can we do partition elimination on them? Okay. So let's look at these examples. So we'll just clean this up a little bit. So we're looking at number 20. Okay, and it has a variation we want to show. The first thing we show is number 20, a little bit of setup we did. Okay, what we're going to do is just create a non-partitioned version of the sales table by selecting the original one, what was the original partitioned version of the sales table. And then we're going to create an index, okay, on the time ID on that table, just to have an index on it. And then we'll have a look at it. Now, if the index was selected enough, based on the predicates we gave it, it could use the index to reduce the query. If it's not selective enough, it may choose to do a full table scan. So let's have a look at, and for this, because we were just showing it, we didn't show doing this. So the next one up is the queries we're actually going to test on it. Okay, so now that we got the setup done, we're going to do a sum of quantity from our non-partitioned version of the sales table using the time between a group of times. Times in 1981-01 to 1981-12-31. Looks like about a year's worth of data to me. No, about 8 years worth of data. We're going to cross 8 years in this case. Okay. Then we're going to do it against the original partitioned version of the table without using any qualifiers. And then we're going to add a request to do it as a parallel operation. And when we access the partition sales table, we want to do for slaves. And we're going to see what happens when we do that. So let's look at the output. So the first one was doing our query against the non-partitioned version. It ended up touching 41 blocks in query mode. Okay, and it touched a couple blocks in parse, but I'm really interested in the fetch to see how much it took to retrieve the data. And it did that many blocks because it did a full table scan of the non-partitioned table. Okay. Second pass is we're going back to the original table that has the same data, but now it's stored as a partition table, except they have a few more partitions than the 4 I drew on the board. But it's just an extension of it. Okay. And in this case, we reduced the data we needed to look at. We only had to touch 308 blocks compared to 44. And the reason why is that we did a full table scan, but only of certain partitions. There is a group of partitions. We only had to scan partitions starting with 5 and ending with 8. That's what the 5 space 8 means. There were ones before it. There's partitions, logical partitions 1 to 4, it was able to drop. And there may be partitions above it, because the time goes further in time forward in time, so there's ones above it. We only had to look at a subset where it reduced the data. That means we had to look at less logical blocks in memory. But when we do this, it basically does it serially, because we iterate over one partition at a time. We do partition 5, and then the same process does partition 4, then does partition 7, and then 8, so to process the 4 partitions. By specifying the hint that says, let's do the query against the sales table in parallel, and let's use 4 slaves, we could actually use 4 slaves. And I guess I shouldn't change my query, but oh well, I won't save it. Sorry, I messed up the hint. I got the bracket in the wrong place, but oh well, we had already executed, I just won't save it. We did exactly the same query, but added a hint. Now we got a further reduction in blocks we had to touch at. And even nicer, we see a nice reduction in time. We reduced the time by an order of magnitude by using 4 processes. To do it in parallel, they can all be looking at different partitions. We can put a slave per partition. Each of them can be working in parallel. Now, the prerequisite is to have all 3 resources a program requires in abundance. You need CPU cycles to run extra processes, so you need extra available CPU cycles. You also need extra available memory cycles. You also need extra available I/O cycles. If any of them become constrained, then you may not see a reduction in time. In fact, my experience, it goes the other way. It increases in time. If we start swapping and paging a lot because of memory constraints, that's going to hurt us more than doing it serially in reality. But if we have it, we've got an ability to reduce the time in the overall processing of it. And it's doing the PX. The original process I do the query from becomes a parallel coordinator, and he gets a group of slaves that process each partition, because there's 4 partitions we're processing, 5 to 8. And each of them gets to read through the data for 1 partition. Makes it very nice to do the query faster. So that gave us a nice advantage of doing them in parallel.